Hello everyone. And so we start the fifth webinar for 2025. This is circular motion, and this is for year 12. So first of all, we want to know which variables. I want to go through which variables we use when we talk about circular motion. Well, if something is moving in a circle, obviously you want to know the speed. Yes, so v is the speed of something going in circles. So v, lowercase v, is the speed. Then you want to know how quickly it can do one whole rotation, and that is called a time period. Time period. Period. Then you want to know the radius. R is the radius of the circle uh, around which you go. Okay. I'm sorry, there's a future physicist. Okay. Radius, if you're going around the circle with speed v, time period, frequency f. Frequency is how many rotations per second. So it's rotations per second. Okay. Time period, time for one rotation. What else? Well, angular frequency. Angular frequency. Oh, angular speed. Angular speed is the angle you turn through per second. Is the if you draw a line from the center of the circle to your position, as you move around the circle, the angle that you swipe, angle swiped in 1 second. Okay, and equations, of course. If you're moving with speed is distance divided by time. So a whole circle, the circumference of the whole circle is 2 pi r. So the speed is 2 pi r divided by the time period. Or in other words, the time period is 2 pi r divided by v. That's a very useful relationship. So if I ask you, for example, how fast does the Earth spin around its axis at the equator, you could very easily calculate that because you can know the radius of the Earth, you can work out the circumference of the Earth, and you know that it does one rotation in 24 hours, so you can work out the speed, and it's about 500 meters a second-ish. Okay, so then the time period, so if the time period is 1 divided by frequency, if how does that make sense? Well, and frequency is 1 divided by time period. Frequency is how many full rotations in 1 second. If t is the time for one rotation, then this formula makes sense. Hopefully I don't need to go deeper into that. And then finally, angular speed. Well, the angular speed, I'll just give you the formula without a proof, is v divided by r, or in other words, v is omega r. And of course, we use centripetal acceleration. So centripetal acceleration. If you're moving in a circle, your speed might be constant, but your velocity is changing. And if your velocity is changing, that means you are accelerating. And your acceleration, turns out, is equal to v squared divided by r. But if you substitute v equals omega r, you get another formula for centripetal acceleration, and it's omega squared. So these are the two formulas. So these are formulas that we will use. Some of them we'll use today. And the next thing I want to talk about is centripetal acceleration. Now, how do you derive centripetal acceleration? So imagine you are moving in a circle. So as I said, because when you are moving around a circle, your velocity is changing. Velocity is changing, and that means um, you're accelerating. Okay, so let's say at time t equals 0, your velocity is this v. Let's call it va, and you're at point A. After some time, you have traveled to point B, and your velocity is different, is vb. Okay. Now, these are vectors, and you've studied vectors. The modulus of VA is equal to the modulus of VB, but the direction has changed. Okay, and we let's say that this angle is theta, and if you recall, okay, this angle is theta. Let's find the difference. So if this vector is VA and this vector is VB, then this vector is VB minus VA using vector addition rules, or it is also known as delta V, change in velocity. So your change in velocity is the final velocity minus initial velocity, so delta V. And we know that acceleration is the change in velocity divided by change in time. So we need to evaluate that change in velocity. And the change in velocity, well, we know that this angle is theta, because we know that, because this is 90 degrees and this is 90 degrees. So if you've turned through an angle of theta, then the velocity also changes by an angle of theta. Now this is v and this is v. This is your speed. And then you can use you can, how should I put it? Imagine, okay, yeah. Let's use the cosine rule. Why not? Cosine rule. It's a bit of an overkill here, but why not? Cosine rule. The cosine rule says that the opposite side of a triangle, so delta V squared, is equal to V squared plus V squared minus 2V times V multiplied by cos theta. So delta V squared is 2V squared minus 2V squared cos theta. Now, cosine theta is a small angle. Theta is small. And for small angles, cos theta is approximately 1 minus theta squared over 2. And we're going to substitute that in. So delta v squared is 2v squared minus 2v squared multiplied by 1 minus theta squared over 2. So 2v squared minus 2v squared plus 2v squared multiplied by theta squared over 2. Theta cancels, these cancel. So delta v squared is v squared theta squared. Okay. And now we just need to work out what theta is. And if you the distance that you travel, this distance, this arc, is v multiplied by t. So length of arc is v times t, because you're traveling at speed v for a time t. So this is t equals t. And then we know that the relationship, because this is the radius of the path, and vt is equal to r theta. So from here, theta can be expressed as vt divided by r. And we're going to substitute that in. So delta v squared equals v squared multiplied by, sorry, it's delta t, of course, delta t, delta t, delta t, delta t, delta t, v squared times v squared again. Okay, v squared multiplied by delta t squared divided by r squared. And now we can divide both sides by delta t squared. Delta v divided by delta t squared is equal to v to the power 4 over r squared. Square root both sides. Delta v divided by delta t is v squared over r, or in other words, which is also known as the acceleration. I think I've done a slight overkill with the cosine of the small angle, but we have managed to prove that centripetal acceleration is in fact the centripetal acceleration. So conclusion. If you're moving in a circle with constant speed, your acceleration is towards the center of the circle, and it's equal to v squared over r, or you can write it as omega squared r. So that is the proof. And hopefully you get that. I've done this webinar a couple of times. So if you go to our YouTube channel, you can find Year 12 webinars, and you can find last year's webinar if you're still confused. Okay, problem 1. A small coin rests on a horizontal turntable. So we have a horizontal turntable rotating and 10 centimeters from the center, there is a coin. The coefficient of static friction between the coin and the surface, so the coefficient of friction is 0.4. Find the maximum angular speed of the turntable before the coin starts to slide. So you can imagine if you spin too fast, the coin will slide off. So, well, I don't need to explain. If you put a coin here, if you spin the book slowly, the coin stays on the book. But if I spin really fast, the coin will fly off. Some people say it is because of the centrifugal force. Now, it is very unlikely that you understand centrifugal force at this time in your life. There's a good reason why centrifugal force is only studied at the second year at university, typically, sometimes in first year, sometimes in third. So if you really want to get your physics teacher upset in school, say two words, centrifugal force, and okay, don't get your teachers upset. Don't say those words, but they will get upset if you mention centrifugal force. The reason for that, because centrifugal force is an imaginary force which only exists in non-inertial frames of reference. And until you understand non-inertial frames of reference, you're going to have a bad time understanding centrifugal force. And that's why centrifugal force is not studied in school physics. But anyway, a coin. So the coin is moving in a circle. So it's performing it's performing a rotational motion. It's going in it's uniform circular motion. In order to do that, it has to have a force towards the center. Because if it didn't have a force towards the center, it would just fly in a straight line. The coin would move in a straight line if there was no force. So as the coin moves, I'm view from top, plan view. You have the turntable, and you have a coin, and at different points, there's a force towards the center. And the only force that is providing that is the centripetal force, is the frictional force. So it is force of friction. Because if there was no friction, then the coin would just fly off the book. Okay. So centripetal force is friction. And that's really important to understand. And therefore, the friction force is mv squared over r, because it's the mass of the coin times the, yeah. And then we look at the coin. So let's look at the coin in this position. So here's the coin. There's a gravitational force acting downwards. So we're now looking from the side view. There's a gravitational force on the coin. There's a normal reaction force, and there's a friction force. So the coin is trying to fly off the book, and there's a frictional force pushing it towards the center. And with the frictional force, we know that it has a limiting value of mu n. So mu times the normal reaction force is mv squared over r. And n, we know that n is mg. So mu mg is equal to mv squared over r. Therefore, of course, it says maximum angular speed. So not speed, maximum angular speed. So mu g equals omega squared r squared over r. So mu g equals omega squared r. So omega max is square root of mu g divided by r. And we can work that out as 0.4 times 10 for simplicity, divided by the radius, which is 10 centimeters, 0.1. And so that's 4 square root of 40. Square root of 40, that's 6.3 radians per second. And the speed of the coin is omega times r, which is 6.3 radians per second multiplied by 0.1 meters is the radius, which is 0.63 meters per second. That's the maximum speed of the coin, which is quite reasonable. A satellite is orbiting the Earth in a circular orbit at a height of 600 kilometers above the surface. Assuming the radius of the Earth is 6,400 and g at the surface, find the orbital speed of the satellite. Oh, I didn't notice that this is let's say at a low circular low orbit. Okay, low orbit is typically under 100 kilometers. We can assume it's just really small. Um, a low orbit. Now, low orbits is the minimum orbit where the effect of air resistance is negligible. But for simplicity, we can just assume that it's equal to the Earth's orbit or Earth's radius. So we just use 6,400 kilometers. Otherwise, we get into trouble with changing g because g changes as you go further away from the Earth, and I don't want to go there. Okay, not today. So let's say it's a low orbit, and there's a satellite, and the satellite is moving around the Earth, and we can have a look at it like this: FET or orbital motion. So this is how it looks like. Model. This is a satellite, and you can see that the satellite goes around the planet. The speed is constant. The velocity obviously changes because the direction changes. And you can see there's a force towards the center of the Earth. The force is always perpendicular to the velocity. It has to be that. Let's try removing that force, remove gravity, and watch happen. Look what happens to the satellite. Oh, so switch gravity back on, press play, and now. So the satellite goes in circles because of gravity. If there was no gravity, it would be flying in a straight line. Hope that makes sense. Okay. So let's say it's a low Earth orbit. We can write directly on here. Low Earth orbit. And yeah, so that force, that gravitational force on the satellite is equal to mg. On the other hand, we know that it is moving in a circle, therefore the centripetal force is mv squared over r, but Fg is Fc, gravitational force is the centripetal force, therefore mg equals mv squared over r, and mass of the satellite cancels out, and the speed of the satellite is square root of gr, which is 10 times 6,400 million meters, which is 8,000 meters per second. And that's the speed of a satellite. That's the speed that you need to go in orbit. Actually, it's a little bit less. It's 7,800 meters, 7,800 meters a second. But that's not the point. That's 8 kilometers a second. 8 kilometers a second. That's the speed that you need. It's this period, A, B. Period is, we all know that period is 2 pi r divided by the speed. So 2 times 3.14 times 6,400 kilometers per second. I'm going to do it in kilometers. Why not? Divided by 8 kilometers a second. So 8 kilometers a second. And then simply just kilometers cancel, and we get something. 2 times ooh, 2 2 times pi times 6,400 divided by 8. 5,030 seconds, which is approximately 1 hour minus 3,600 divided by 60 and 24 minutes. 24 minutes. Cool. So about 84 minutes. About 84 minutes. And let's check if that is realistic. So period of the ISS and International Space Station orbital time period is about 90 minutes. It's slightly more than 84 minutes, but because it's a slightly higher orbit, we assume that it just follows the Earth, which is obviously not possible. Like in the minimum orbit is about 100 kilometers. But that makes sense. Okay, moving on. A stone is whirled around in a horizontal circle on a string length of 1.2 meters. Okay, it completes. So there's a stone in a going in a circle. 5 revolutions per second. Find the tension in the string. So the tension in the string. So tension is the centripetal force. So in every question, the first thing you do, you identify which force is centripetal force. Tension is the centripetal force, and therefore you can say tension is mv squared over r, and then you start working out. So the r is 1.2 meters, 5 revolutions per second. That's frequency. Frequency is 5 hertz, 5 revolutions per second. So what can we use here? We can find the time period is 1 over 5, which is 0.2 seconds. And the speed is 2 pi r divided by time period, which is 2 times pi times 1.2 divided by 0.2, which is 12 pi, about 30, about 40. 2 times pi times 1.2 divided by 0.2. 37.7 meters per second. That's the speed. And the tension, ooh, that's very bad. I'm using tension. I'm using tension and I'm using time period, same letter. So the force of tension, the force of tension, force of tension, force of tension is mass times velocity squared divided by r, which is oh, it doesn't give the mass. Okay, so that's 20 grams. So 0.02 times v, which is 37.7 meters per second squared. This is kilograms divided by radius, which is 1.2 meters, and magically 0.02 times 37.7 squared divided by 1.2 is about 23.7 meters newtons. Well, that's quite a large force. Quite a large force for well, it has to be because the speed is really big, right? 37 meters a second. Okay, I just realized 37. A car on the motorway is about 25 meters a second, so it's a really fast stone. What are you going to do about it? Okay, question 4. A car moves around a flat circular track. The coefficient of static gravity of the tires in the road determine the maximum speed at which the car can move without skidding. So, car taking a turn. Apologies. Apologies. So, a car going around the corner. Sorry. A car going around the corner, and let's find a picture. Car going around a corner. Okay. So this is the radius of the curve. So we can say that this is the radius. And the force that is pushing the car towards the center of the bend is the friction with the tires. So there are four tires, so there's friction, force of friction. And we know that there's mg acting on the car, gravitational force. There's a normal reaction force. And we know that the force of friction is the centripetal force. Petal force. So just like with the coin, it's a very similar question. Sorry. So mv squared over r is equal to mu n. And just like with the coin, mv squared over r equals mu times mg. M cancels, and v is equal to square root of mu gr. Okay. And that's the maximum speed that a car can go around. Right. Okay, moving on. A bead of mass slides by friction on a circular wire loop over to a vertical plane. A bead vertical plane. Okay, so we have a loop, and we have a mass, this a bead, that goes around a vertical circle. Now, it is the bead is released from rest at the top wire loop. So a bead is on the wire. Apologies. Yes, and it's released from rest. So it's released from here with zero speed. And as it falls, it accelerates. It accelerates because gravitational potential energy gets converted to kinetic energy. So gravitational potential energy at the top, so the height at the top is 2r. So gravitational potential energy is 2 mgh. So mg multiplied by 2r is equal to the kinetic energy, which is mv squared over r. M cancels, and we get the speed is equal to, oh, sorry, over 2. Kinetic energy is 1/2. Is square root of 2 is 4 gr, or 2 root GR. When I say hi. Okay. Sorry, I've got a young daughter and she's very keen on uh, right, physics. Okay, so yes, the speed at the bottom of the loop when it reaches is 2 square root of gr. So we've established that. And now we need to find the speed. So we found it, find the speed, and the normal reaction at the bottom of the loop. So what do we mean by normal reaction force? Well, at the bottom, at the lowest point of the loop, there are two forces acting on the bead. There's the gravitational force, so the mg, and then the normal reaction from the wire. Now, because it is moving in a circle, there has to be a centripetal force. So the centripetal force, force is the normal reaction minus mg. Oh, say hi. Say hi to everyone. Oh, okay. Centripetal force is normal reaction minus mg. So is the force going into the center minus the gravitational force. Sorry, meeting's getting hijacked. Um, okay. Right. So centripetal force is N minus mg. And centripetal force is mv squared over r equal to normal reaction minus mg. And therefore, normal reaction force is mv squared over r plus mg. And we know that v squared is 2gr, so m multiplied by 4gr divided by r plus mg. R cancels, so it's 4mg plus mg. That's equal to 5mg. So the normal reaction is 5 times greater than the normal reaction force. Oh, sorry, the gravitational force. Normal force at the bottom. Yes. Okay. So hope that makes sense. A pendulum of length 2 meters swings through a maximum angle of 60 degrees. So we have a pendulum going like this, back and forth, and through a maximum angle. So I'm assuming this is 60 degrees. Okay. And the maximum tension in the string if the mass of the bob is 0.5 kilograms. Right. So if this is 60 degrees, then we can say that this is 30 degrees. And we need to calculate. So when it reaches this point, it stops. It momentarily stops. So we want to know this height, the change in height, first of all. And if we draw this, so this is the length of the rope, and this angle is 30 degrees, then this distance is L cos 30. And because the whole height is L, then this small change, H is L minus L cos 30, which is L 1 minus cos 30. It's a very useful expression. You will use it a lot in this assignment as well. So yes, if a pendulum swings by an angle theta, the height at which it swings is L times 1 minus cos theta. And that's your gravitational energy. So gravitational potential energy at the top of the swing is mgh, which is mg times L 1 minus cos 30 degrees. Then kinetic energy, of course, at the bottom, because you have conversion from gravitational to kinetic. So it's 1/2 mv squared. And therefore, you can work out the speed. Speed at the bottom is, so 1/2 mv squared is mgl 1 minus cos 30 degrees. M cancels. V is equal to 2gl 1 minus cos 30 degrees square root. Do we know the length? Yes, we know the length is 2 meters. So it's 4g. So square root of 40 times 1 minus cos 30. So cos pi over 6. My calculator is in radians for some reason, which is 2.3 meters per second. That's the speed of the pendulum at the bottom of the swing. Speed at bottom of swing. Okay. And then we can find the tension again. So at the bottom of the swing, there are forces. So there's a there's a gravitational force, mg, and there's the tension force, T. And we know that it is accelerating upwards. The pendulum is accelerating upwards. So we can say that mv squared over r, the centripetal force, is tension minus mg. And so the tension is mv squared over r plus mg. And it's equal to m, which is it's 0.5 kilograms, 0.5 times 2.3 squared divided by 2 plus 0.5 times 10, which is 0.5 times 2.3 squared divided by 2 plus 5, which is 6.3 newtons. A very reasonable force. Okay, what else do we have? A car. I think this is the last one we'll do. Okay, a car of mass 800 kilograms drives over top of a hill. So a hill which looks like this. And there's a car. Best drawing of a car ever. So 800 kilograms over top of a hill, and it's an arc of a radius of r. Find the maximum speed at which the car can drive without losing contact with the road. Well, what do we have here? Well, we have two forces acting on the car. There's the gravitational force acting on the car, which is mg, and we have the normal reaction from the road, which is pushing upwards. But because the car is moving in a circle, it's accelerating downwards. And this is centripetal acceleration. And we write Newton's second law. Newton's second law says mass acceleration is equal to mg, it's accelerating down, mg minus n. But acceleration, we know it's mv v squared over r, and it's equal to mg minus n. Now, when the car loses contact with the road, when the car loses contact, you can imagine if the car goes really fast, it will just fly off. When the car loses contact, n becomes 0. And we can solve for that. So we can say, well, very good. And v squared over r equals mg minus 0. Therefore, v squared over r equals mg g. So v is equal to square root of rg. And that is the answer. And $50 meters, square root of 50 times 10, which is approximately 23 meters per second. Let's see how well I can do stuff. Okay, 22.3. 22.3 meters a second. Okay, so that's how fast the car can go without losing contact. Now, what happens if the car goes faster than that? Because you can see that the normal reaction, so this force between the car and the road, the contact force between the car and the road, N is equal to mg minus mv squared over r. V squared over r. So you can see that the faster you go, the less there's the contact force. So contact force decreases as the car goes faster. You can see that from the equation. If v increases, then n becomes smaller. So at some point, n becomes 0. So when n becomes 0, you have this expression. 0 equals mg. So when n is 0, mg minus mv squared over r. And then you have mv squared over r equals to mg. And if you look at this equation, there's one thing that always, which looks quite interesting. Anyway, if you the car can go even faster than that. So imagine the car goes even faster. If the car goes even faster, then this term, the v increases, but mg is constant. So this is constant. So how can the speed increase if this term is constant? Well, as a matter of fact, if this is the shape of the road and the car goes faster, it actually loses contact and starts moving in a bigger circle. So the radius increases. So this is the radius of the bridge or the radius of the hill, but this is the radius of the car. So v increases. So as v increases, r also increases. And so this term remains constant. Okay. I sort of rushed through this because I had very little time. We had very little time left after the launch webinar. So hopefully that was useful. I do recommend you going back to our YouTube channel. Well, you can find it here. So if you go to COMPOS, so if you go to our website, so this is our website. If you go to About COMPOS webinars, and then year 12 webinars, first of all, this is the timetable for the whole year. So next webinar will be on the 12th of November. It will be on trig identities. And here on the bottom, you have YouTube playlists. So all Year 12 webinars and the Year 12 whiteboard, the whiteboard I used today that you can access. Now for if you can also click all Compos webinars to see all webinars from all years. Yes. Okay, so I hope that was insightful, useful, etc., etc. I hope you enjoyed it somewhat. I hope I've managed to share the love of physics with some of you. And yeah, looking forward to seeing you in 2 weeks, 2 weeks from now, and enjoy the Compos course. People say that it has been very rewarding and yeah, very challenging also. All right, so welcome to Compos, people who I haven't seen before, and yeah, see you in 2 weeks. Sorry that I didn't manage to answer all questions. Uh, please come back next session and ask them again.